Hello, my name is Sujoy Ganguly. I'm head of the Applied Machine Learning Research Group at Unity. And I'm going to talk to you today about how we can use synthetic data to create custom computer vision data sets that expand the access of computer vision data without compromising privacy. I'm going to start today with a brief introduction into training with real-world data, as well as training with synthetic data. I'm going to then go into talking about the methods that we can use to bridge the gap between synthetic data and real data. And finally, I'm going to end today with a discussion of some benchmark environments and tools that we're providing to the community to advance research into this problem on how to train with synthetic data on real-world tasks. So in a typical computer vision workflow, we acquire real-world images. We label and annotate them, often painstakingly. We then train our computer vision models. We then evaluate the performance of our models. And if they're good enough, we deploy those models to production. And then the bane of everybody's existence is in production, we find out there's a problem with our models and realize we have to go back and acquire more data, get it relabeled, retrain the model, and reevaluate. And therefore, oftentimes in any computer vision product, we're spending 70% of our time collecting data, labeling it, annotating it. And that's because training with real-world data is challenging. It is expensive to acquire. It is time-consuming to label. Because it's expensive and time-consuming, it is often biased and insufficient. And sometimes it is not privacy compliant. Synthetic data can be an answer to this problem. Synthetic data is automatically labeled, so there's no human annotation or labeling required. It is privacy compliant because it is synthetic. It is iterative because it's programmatic. It is affordable because it just simply takes content and environments and not large-scale operational teams. And it can be representative because you have control over the distributions of data that's being generated. So in a synthetic data workflow, you sort of have something slightly different. You build the environment, you then generate automatically labeled images, you then train your computer vision model, you then evaluate your model as before, and you deploy your model. But here, when there's a problem with your data, your model's not performing in certain scenarios, you can simply go back to your environment and request new data. If you need better labels or different kinds of labels, you can just ask for better, different kinds of labels, and then train, evaluate, and deploy your model even faster. And one of the ways we use to create these synthetic data sets is something called domain randomization. So domain randomization is a method to create the most diverse data that our machine learning models can learn from by varying various properties of the data set. So for example, the spatial location and orientation of objects, color, texture, lighting of the backgrounds, optical occlusions, camera positions, orientations, field of view, all sorts of things. Typically, we break these variations into two categories: the intrinsic variations and the extrinsic variations. So the intrinsic variations you can think of as sort of features of your target object in an object detection task. So their shape, texture, color. And they can be simple or complex variations. Extrinsic things or things about the environment or the camera or placement and orientation of objects, and are often thought about as unstructured versus structured. Now, depending on the problem that you have, you may live in a different part of this variation space. So examples we like to give are if you're trying to detect a single brand of shoe or a single type of shoe from a specific brand, but you want to be able to detect that in any environment. But because you want to detect it in any environment, we say, well, you should use an unstructured environment, and very simple variations on the target object. However, if you wanted to detect a wide range of objects, like all the types of shoes, again, in any environment, then you say, well, let's have a very unstructured environment, but we need to have very complex and rich intrinsic variations of the shoe. Another example would be if you're trying to detect a specific set of furniture. Again, because it's a specific set of furniture, the variations of that furniture are pretty simple. But because it's in a home and because furniture itself is laid out in very structured ways, you need to structure your environment so the extrinsic variations become very structured. And if you're trying to detect a person in a home, sort of the hardest version of the task, which you need a very structured environment, the home, and a very complex, rich set of intrinsic variations. In this case, people, their different clothing, hair, skin tones, etc. Therefore, domain randomization, though a useful technique, does provide a certain burden on how you generate this content. Specifically, it establishes sort of a levels of content in machine learning. So that is visual. So that is your content needs to render correctly on a wide range of conditions. The appearance needs to be able to be varied. Again, the intrinsic variations. So that means those textures, those materials need to be changed, and they need to be changeable programmatically. You also maybe need a physical reality. So your assets might need to be able to interact, collide with other objects in the scene. That would depend on their mass, their density, their friction, etc. And all of these should be variable depending on the scenario. You also might need kinematics. So objects need to be rigged and animated. Objects of the same class should share rigs and animations, and these animations need to be varied. And finally, of course, we have fully embodied content, which is not only visual, physical, and kinematically realistic, but also has to react to the actions of other agents in the scene. So this is really, really hard in principle, so we're providing some tools to make that easier. So the first is the perception package. Here you're seeing some images rendered from the perception package with a variety of bounding labels for bounding boxes, instance segmentation, 3D bounding boxes, semantic segmentation, surface normals, depths. We have LiDAR sensors, we have occlusion labelers, all kinds of rich and varied systems. Additionally, we're providing a ready-to-go environment specifically for human-centric computer vision. What we talked about, humans are quite complex in their variations, so setting all that up is really, really hard. And so we've done that work for you. We provide a large number of assets, animations, clothing textures, randomization systems for controlling placements of objects, backgrounds, scenes, labelers are ready and set up out of the box. It comes with the CLI, so you can change and play with these parameters, as well as ready-to-go binaries for both Mac and Linux. Of particular note with People Sans People are the animation and pose randomizer. So the ways in which you can change the positions or poses of characters in your scene, as well as the clothing and texture randomizer, which is done with a shader graph method, which allows you to vary the clothing texture and even wrinkles on the clothing. This again provides even richer variations. Putting all of these things together, you end up getting wildly variable scenes if you use the default settings that are in People Sans People, and you'll get images that come with bounding box labels, key point labels, as well as instance segmentation labels. As I said, one of the cool things about synthetic data is also the ability to control and measure and change the distributions of your content. So here we're comparing the number of bounding boxes, so people, labeled people in the scene, and we're comparing Cocoa to the PSP data. So Cocoa's in red and PSP's in blue. You can see that using the default parameters, our synthetic data has more diversity in terms of the number of people in the scene, as well as more diversity in the size of people in the scene, which is the plot we see on your left. Additionally, we can control the placement of people in the image. So here, again, in red is Cocoa, in blue is the synthetic data generated PSP. You see in Cocoa a slight funny aliasing effect because not all the images are the same size. But you also see a tendency of people that are labeled in Cocoa to be in the center of the image. In People Sans People, the synthetic data, we see much more uniform placement of people again, at least using the default parameters that we are providing. We also have enhanced pose diversity. So here you're seeing the distribution of key points. Again, red is Cocoa, blue is people sense people data or synthetic data. Here you're seeing just 5 of the key points. You can see our paper for all the key points, but here we're just showing you the nose, the right wrist, the left wrist, the right ankle, and the left ankle. And here we've also done a thing where we've put 0, 0 is the mid-hip of a person, and the length from mid-hip to the neck, so the torso length, is 1. So doing that, we're able to see that in real-world data sets, Cocoa Humans data set in red, that there's a tendency for people to be front-facing, facing the camera, as opposed to in the synthetic data set, again, using the default parameters, this bias is eliminated. We have people facing front as often as behind. We also have a wider range of poses available because we've sampled from a very diverse set of animations. Additionally, we have improved label consistency with synthetic data. So here you're looking at the number of key points that are labeled per person in Cocoa versus People Sans People. You see in general in People Sans People, synthetic data, you get all 17 Cocoa key points labeled, whereas in Cocoa, you actually get, most of the time, none of the key points labeled, and very rarely do you get the full set of key points. Now, you also see that in synthetic data, sometimes you also don't get all the key points, and that's because of occlusion. So here, we've turned on the occlusion setting so that even if a key point is hidden by a person themselves or another object, it's not being labeled. This can also be switched back on so that you can even see those if you want, because synthetic data, it's just a matter of changing something in the command line. We also see an improved consistency in which key points are labeled. So we see that all 17 key points tends to be labeled with the same probability in synthetic data, again in blue, versus in Cocoa, where you have a tendency to label the center of the body more than the full body. Now, to see whether or not these wildly diverse data is actually useful, these default parameters are useful, we're going to do a very simple baseline training experiment. So we're going to generate data from People Sans People using the default parameters and train a model from scratch using synthetic data. We're then going to fine-tune the model on the target real-world data, in this case, Cocoa. There's not going to be any weight freezing or clever tricks here, just standard pre-training and fine-tuning. And then we're going to evaluate to start with on the Cocoa test data set. So here you can see the results for both bounding box and key point precision. Training from scratch means we trained only on Cocoa data. ImageNet pre-training means we used the pre-trained ImageNet backbone, then fine-tuned on Cocoa data. And synthetic pre-training means that we trained on 490,000 synthetic images and then fine-tuned on Cocoa data. We see, unsurprisingly, of course, that as you increase the amount of real-world data, that models get better. However, we see that when you have very little real-world data, synthetic pre-training is incredibly good. And as you get more and more real data, it still is better than any other pre-training method. And that holds for both bounding box and key point precision. Now, what does that mean? It's great to talk about, there's some number called key point or bounding boxes. What it means is that we're eliminating false positives. So here in the top row, you see the ImageNet pre-training. Here we're showing just with 6,411 Cocoa images. And you see that for some reason, an ImageNet pre-trained model fine-tuned on Cocoa thinks that this mouse and plane are people, whereas something that's trained with synthetic data does not have that problem. Furthermore, we see that the key point predictions tend to be more accurate. So again, top row is ImageNet pre-training, then fine-tuned on 6411 Cocoa images. In the bottom row, we see synthetic pre-training. You see things like the elbow key point accuracy improving, less confusion about where wrists are and about knees. And in general, we see that as we increase the amount of synthetic data used in pre-training, that our models improve after fine-tuning. So here you're seeing the size of synthetic data. Different colors is the amount of fine-tuning data used in Cocoa. And here we're just showing the key point accuracies of the models. And for comparison, this is what ImageNet pre-training would look like. Now, though these fine-tuning results show that synthetic data provides this distinct advantage in real-world performance, it does still also highlight that the zero-shot performance is pretty bad, that you do need to fine-tune. Now, how about generalization? So here we're looking at the results of that same model, but now tested on data sets that are not COCO. So this is a model trained on synthetic data or ImageNet or pre-training, then fine-tuned on COCO, and then tested on 4 other human-centric computer vision data sets, the MPII dataset, CrowdPose, leads, and occluded humans. In general, we see that models trained with synthetic data outperform those trained on real data alone out of distribution, as they did on the COCO test set. And we can even see that with as little as 5,000 images, a synthetic data set performs as well out of distribution, so generalizes as well as a model trained on ImageNet. Now, one of the data sets we've compared there is another synthetic data set called MOTSynth, which is far more structured than PSP is by default. So MOTSynth is a data set generated using the GTA 5 game. It's specifically designed for multi-object tracking, specifically multi-human tracking, comes with a wide range of labels, and was published at ICCV in 2021. Returning, we can also see that if we compare our wildly diverse human-centric data to MOTSynth, which is again very structured and task-specific, multi-object tracking tasks, we see our wildly diverse data actually outperforms in generalizing as well. So wildly diverse data that is task-specific seems to improve the generalization of models compared to very structured or specific data sets. So in conclusion, synthetic data can be the future of model training, but it's hard to make. Therefore, we are releasing People Sans People, as well as the Perception Package, which are 2 open source tools to allow people to work on synthetic data and understanding the sim-to-real gap. We've also shown that synthetic pre-training outperforms real data pre-training across a wide range of data sets. But we also have demonstrated that zero-shot performance is poor and may improve with more structure. And this begs a question, can we learn the optimal set of parameters that allow for both out-of-distribution performance and zero-shot performance? And we hope that the research community will pick up that question. And I'll leave you with links to both our papers and GitHub pages for you to try this stuff out for yourself. Thank you.